Second video from the first lesson of Chapter 1. In the first video we talked about these four things, and I'll talk about one-to-one and onto, continuous and discrete, or linear and nonlinear. We've talked about how if each input goes to only one output, it's called a function. So here's a mapping with a relation, and each input's going to only one output, so it is a function. But a function is called one-to-one, which we write this way but call one-to-one, if every input only comes from one output, meaning each output is only pointed to one time. So here each output only gets pointed to once. 8 only came from 5, 4 only came from 6, -1 only came from 1. So this is called a one-to-one function. The other example I have over here, give me a second to type this out, excuse me. The other example, if you look at the number 6, this is a one-to-one function here, but over here, if you look at the number 6, -2 goes to 6, and -5 goes to 6. Now this is still a function, because each input is only going to one output, but it's not a one-to-one function. This input goes to 6, this input goes to 6, so there's two things going to 6. 6 is pointed to 2 times, so it's not one-to-one. With that in mind, pause for a second, look these over and determine if these are one-to-one functions or not one-to-one functions. Here 1 goes to 8, 2 goes to 6, 5 goes to 2, 6 goes to -1, and 5 goes to 4. Since 5 is going to 2 and 5 is going to 4, this can't be not a function at all. If it's not a function, it can't be a one-to-one function. Here, each output is only pointed to one time. I mean, 5 goes to 2 twice, but that's just basically listing 5 to 2 and 5 to 2, listing the same point twice. It's not changing anything. Since each input only goes to one output, and each output only came from one input, this is a one-to-one function. Here, 2 goes to -10 and 2 goes to 2, so it's not a function at all. Here, every input is going to only one output. 1 goes to 6, -5 goes to 6, -3 goes to 6. But since they're all going to 6, this is a function but not a one-to-one function. Because basically, if you drew a map, there'd be a bunch of things pointing to the same number. When that happens, it can still be a function but not a one-to-one function. It's actually easier to tell if a function is a one-to-one function by looking at a graph. We've talked about the vertical line test. The vertical line test tells you if a graph is the graph of a function. So here this passes the vertical line test, so it's a function, but it's going to fail the horizontal line test. Here's a horizontal line. The horizontal line hits this graph more than once. And since it hits the graph more than once, like here there's the point -6,4 and the point 2,4, 2 is going to 4 and -6 is going to 4. So this is a function but not a one-to-one function. This one's not even a function because it fails the vertical line test. This one passes the vertical line test and it passes the horizontal line test. So it's a one-to-one function. It's worth noting that for something to be a one-to-one function, it has to be strictly increasing or strictly decreasing. By that I mean if I have a function that goes up for a while, but then starts to go down and then goes up again, at any point where it goes from up to down or from down to up, you're going to fail the horizontal line test. So it has to be only increasing or only decreasing as you look at it from left to right. Another thing discussed is if the relation is continuous or discrete. A continuous function or continuous relation is one that has no jumps in the graph. There's no breaks anywhere. Basically, I can get from one point to the next by passing all the space in between, or some people think I can graph this without ever picking up my pencil or picking up my stylus, as it is these days, off the page. But this discrete one over here has jumps in it. If I were to try to graph it, I just have to go point and pick up my pencil and point and pick up and point and point and point and point. And I don't actually pass the space in between all the points, which means that this is discrete and not continuous. One way to think about it is, can you hit every single point? Could you have like a 1.1 or a 3.8 or a 22/7 or something like that? Could you hit every single possible point in between? Not just the whole numbers, or not just the even numbers, or not just the fractions of the denominator of 5 or something. So when a relation can be discrete, it doesn't happen all that often when we're doing with just straight numbers. Like if you just have an equation like y equals -x plus 7, that's probably going to be continuous unless there's something that changes, like where if we say x is only whole numbers. Well, if x is only whole numbers, this has to be discrete because this function here could never come out to like y equals 3.4. There's no way to make that happen because x can only be whole numbers. So you're discrete if you can get from point A to point B without passing the space in between. I always think about walking. When I walk, I can't teleport. I can't teleport to over here. I can fly maybe, or I can jump, or I can swim or something. But no matter how I'm traveling, I have to pass all the space in between to get from point A to point B. If I'm going to walk a mile, at some point I'll walk 0.5221 miles, and 5.5222 miles, 0.5223 miles. I pass all the space in between. If I could teleport from here to here, then traveling becomes a discrete function, or discrete phenomenon, I'll say. But instead, it's continuous. However, a lot of things that we do in life are discrete. Dwayne Wade can't score 5.3 points per game. He can't score all the points between 0 and 1 points. He just goes from 0 to 1 to 2 to 3, or 2, 4, 6, 11, however he's scoring his points. So here I made up some silly little graph that's like years of points or something. And say that he scored 4 points here, but then 7 points here. He doesn't pass the space in between. He has to jump with these points. Now sometimes we'll connect the dots, and connecting the dots just shows kind of the trends of what's happening. But that's more just for visual aid so that we can see how things are changing, but it can still be discrete in this case. Finally, the last thing to talk about is linear relations. A relation is linear if the graph forms a line. All 4 of those graphs there are linear relations because the graphs form lines, but when you graph a quadratic, it's nonlinear, or anything with any sort of curve, or even with a break in how the line looks. All those green things I just drew were nonlinear. For the record, we call this a constant function because the output value is never changing. The y value is always -2. And this is not a function at all. It's failing the vertical line test where x is -4. X could be anything. X could be -4 and y is 0. X could be -4 and y is -3. X could be -4 and y is 12. Each x has a different y. Each input has a different output. This is not a function. For the record, this is not a one-to-one function. The other 2 lines are both functions and one-to-one functions because they pass the vertical and horizontal line test. You can also tell the function is linear by looking at its table. If there's a constant change from the x's to the y's, this is going down 2, right 3, down 2, right 3, down 2, right 3. It's doing that all the way through. And this means that this table represents a linear function. If it's linear, it's going to be a function unless it's a vertical line. It's the idea of slope. If the change in y is the same as the change in x, if your rise and your run are always the same, you have a linear relation. It's also the idea of proportion. If you took geometry recently, you talked a lot about similar shapes. If I look at this top left graph, it's proportional between any 2 points. I can pick any 2 points on the graph. It's going to give me a proportional, it's going to be similar triangles. Like there's those 2 points, and there's those 2 points. Any 2 points that I pick give me similar triangles because the rise and the run are proportional because you have the same slope. So it gives you a linear relation. To recap, if each input goes to only one output, the relation's a function. If each output comes from only one input, it's a function, it's a one-to-one function. If a graph passes the vertical line test and the horizontal line test, it's the graph of a one-to-one function. If there's no jumps or breaks, we call it continuous, otherwise it's discrete. If it forms a straight line, it's a linear relation, otherwise it's nonlinear. And I think that's enough videos for today.